Welcome to Web Handling. My name is Dave Roisum. I'm super excited to begin a new series on time constants. Time constants are not only useful in many of the general sciences, they can also be a useful concept in certain web handling applications. The product process designer can take these concepts even further and use them to quantitatively predict how long the web or wound roll will take to stabilize to a new condition. In this series, we will cover topics as varied as moisture and temperature changes in both the web and wound rolls, as well as wound roll shape, bagginess, and more. A time constant simply tells us how fast or how far are changes in a physical system that have or will have progressed. The equation is an exponential and is sometimes called exponential decay. Let me define this most simply. A time constant is how long does it take to get most of the way there. Let's unpack the words with our simple definition. Long is simple. It's just the time measured in anything from seconds to years. Most is what you think it is, more than half. Specifically, one time constant is 62% of the way to getting to its final state. Let's use an example of a cup of boiling water cooling to room temperature. One time constant, or most of the way, is when the water cools to 50 C, which is 122 degrees Fahrenheit. If we wait longer, specifically 2 time constants, the cup of water is cooled to 31 C, and in 3 time constants, it has reached 24 C. After 5 time constants, the system has reached 99% of the way to its final state. In our example, the cup of water is now only a half a degree above room temperature. In other words, far, far closer to its end state room temperature than where it started boiling. There are many applications in science for the concept and the math of the time constant. The classic example you would be most familiar with might be nuclear decay, with a half-life being slightly less than 1 time constant. You may also be familiar with the charging and discharging of a capacitor in an RC circuit. Time constants will also apply well to certain web handling issues. What we will not cover in this series is dimensional changes due to polymer crystallization or curing. What we will cover in upcoming episodes are moisture and temperature changes in both a web and wound roll. We will also mention internal changes in wound roll stresses and external changes in shape due to handling and storage. So, what do you need to know to do the math, if that's something you're interested in? Since the equation has 5 variables, we need to know 4 of the 5 to predict the 5th. This means we have a lot of flexibility to solve different problems. These 5 variables are time, the time constant for that system, the number of time constants, the starting value, and the ending value. No worries. We will give several common and practical examples in our next episode. What is usually the case is to infer the time constant from one experiment and one measurement for one system. Then we decide how far is far enough. Finally, we calculate how long it takes for that system or a very similar system. No worries, kiddos. We're going to make this as absolutely painless and practical as can be. The focus of this series will be the concept and the approximate times for various common situations. Only very occasionally will we outline how to get time constants to do the math and thus the prediction. I hope you've enjoyed this introduction to time constants. Stay tuned for next week's show when we describe one of the simplest and best studied of time constants for web handling, that is, moisture changes in a web. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. See you next time.